Okay, back for part two. So we're just going to talk a little bit about atomic mass units for just a few minutes here, and then we'll move on to isotopes. So the mass of an atom in atomic mass units is the total number of protons and neutrons in the atom. So in the last segment, we talked about how to determine the number of protons and neutrons. And so a carbon atom with 6 protons and 6 neutrons is assigned a mass of exactly 12 atomic mass units. So what that means is that the atom has these units that contain mass, and they're called atomic mass units. So if we wanted to assign a value to an atomic mass unit, a measurable unit, such as grams, it's defined as the atomic mass unit is 1/12 of the mass of an atom of carbon that has 6 protons and 6 neutrons. So one atom, tiny, 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 and one atomic mass unit is equivalent to 1.66054 times 10 to the negative 24th grams. Okay, so we can see how small that would be. And so then if we took the inverse of that equivalence, we could say that 1 gram is equal to 6.02214 times 10 to the 23rd atomic mass units. So just gives you an idea of the value associated with an atomic mass unit. And of course, atoms are very, very small. So one atom that's made up of 12 atomic mass units is not going to have a very significant mass. So let's talk about isotopes. So definition of isotopes. Isotopes are atoms of the same element with different masses. And so what gives them their different mass is a different number of neutrons, thus the different mass numbers. So this is a very good example. So if I look at the symbol for carbon, the symbol for carbon is carbon 11, and the 6 is the atomic number, which gives me the number of protons. This is the isotopic symbol for carbon 12. Atomic number is 6. The atomic mass number is 12, and so on, 13 and 14. So what we see here are 4 different isotopes of carbon. Each one has the same atomic number, okay, because what does the atomic number identify? From our previous segment, we know that the atomic number identifies the number of protons. And so what we see in each case, if we subtract 6 from 11, what are we going to get? We're going to get 5. So that means I'd have 5 neutrons for that one. If I take 12 minus 6, I'm going to get 6. On this one, I'm going to get 7. And on this one, I'm going to get 8. So each of these values that I just wrote are going to represent the number of neutrons in each of these isotopes. So the isotopes differ by atomic mass number due to the fact that they have a different number of neutrons. Okay, so we can talk about isotopes. We can talk about the mass of these isotopes and how to measure the mass of these isotopes with an instrument called a mass spectrometer. And it very accurately compares the mass of different isotopes of one element. So let's say we have chlorine 37 and chlorine 35. 35 is the more common isotope. And so chlorine 35 being lighter than the chlorine 37, that's the one that's going to be deflected in the magnetic field more than the chlorine 37. You can see here the chlorine 37 doesn't get deflected as much. So this mass spectrometer will give me the relative masses of different isotopes of an atom. So what we say is that different isotopes of an element all react essentially the same. So the element isn't different, but the isotope just has a different mass. And so we look at the weighted average of isotopic masses, and that's something that can be calculated. So the value that you see on a periodic table is always the weighted average of all of the naturally occurring isotopes of that particular atom. And so what I'd like to do is do a couple of examples of this with you, because if you have never done this before, it can be a little bit difficult. So I like to start out with this idea of the weighted average for your course grade. So determining the weighted average for isotopes is very, very similar. So how would we determine a grade that, let's say that the instructor said that tests were worth 50%, and the student's average on all the test grades was 75. Well, I would take 75 and multiply by the relative weight, which I would call 0.5 for tests. So I make my relative abundance, is the word we could use, my relative occurrence of this out of 1 rather than 100%. So then let's say the lab average for the student is a 90, and labs would count, let's say 15%. This is just hypothetical. This is similar to mine, but not exact. And then let's say that this same student has an average of 85 on all of their quizzes, and we're going to call the relative average of that to be 20%, so 0.2. And then the problem sets an average of, let's say, an average of 100, and those are worth 15% relative percent is 0.15. So in order to determine the course grade with these values and these relative weights, then it would be, I'll just figure this out for the fun of it, 75 times, so I take 75 times 0.5, I would add to that 90 times 0.15, I would add to that 85 times 0.2, and I would add to that 100 times 0.15. And I get an average of, when I do that out, 83. So that's how you would work out weighted averages for a course grade. Again, that's not necessarily the percentages I use, but it's just an example. So then let's look at it with in relationship to isotopes. So this example here gives me this information. The element cerium has 4 naturally occurring isotopes, and a very small percent for one of them. And the isotopic symbol for cerium-136, and you use that notation, that rounded value, just to give the isotope a special name, cerium-136. Its actual atomic mass would be this, given here, out to many significant digits. And then the second isotope is here, cerium-138, but that's the specific mass value. And then there's the third one, specific mass value. There's the fourth one. How do I determine the average atomic mass of cerium? Well, here's what I do. I'm going to take, so in the red, I just take each value and multiply by the relative abundance of it. So I'm going to take, instead of 0.185%, I'm going to take 0.00185. So it's out of 1 rather than out of 100%. And then I'm going to take the second one, all the digits given, times the relative percent of it, or out of 1. And then the third, 88%, 88.45, it's going to be 0.8845. And then the same thing goes for the last one at 11.1114. And then in the green, I just did each one out separately. And then following some of the sig fig rules, I end up with 140.1 as my final answer, because what I've done here is I've left all my digits in, but I've looked at my multiplication allows me 3 sig figs here, 3 sig figs here, 4 here, and 5 here. So what I would have to do is I would have to consider the fact that in this, when I can only have 3 sig figs, I can only go 3 places past the decimal point. And that ends up being the scenario for all of these 3 places past the decimal point. This one is going to allow for 4 sig figs, and so it's going to be those 4 sig figs. This one allows 5 sig figs, so there. But now I'm adding, and so my adding tells me I can only go, that rule for addition says I can only go 1 place past the decimal point, because I've gone 3 places here to get my 3 sig figs. Now I can only go 1 place past the decimal point because it's all addition in this step. So my actual answer, according to sig figs, is 140.1. I just thought I'd throw in the sig fig application there. Thought it might be helpful. And then there's another type of problem with these, which is a situation where you're given the fact that there are 2 isotopes. So I'm given the 112.90406, and then I'm given the 114.90388. But I don't know the percentage that they occur in nature. I don't know their relative abundance. So I would call one X, arbitrarily pick one as X. The other one I would pick as 1X, because whatever the relative occurrence is of this one out of 1, the other isotope is going to be 1 minus that value. So then I go through and I do a little bit of algebra. I distribute my value, and I distribute the value here, and I get my expression. Then I combine my like terms, right? If I combine my like terms, I get this value, and then I pull this over to the other side. So I subtract it from this side and subtract it from this side. I keep track of my signs. I do a little algebra, and I get my X value. So my X value is the number 1 isotope, and my 1 minus X value here is going to be the number 2 isotope, and so I did that here. So again, it's out of, this is just the relative occurrence out of 1, and so then to make it out of 100%, because that's how you typically would report your abundances, not out of 1, but out of 100%. So I'd multiply that value by 100. I multiply that value by 100, and that's how I get my 2 final answers. I'm going to stop right there.